What's controlling your destiny right now? Tonight, we're going to explore the invisible force that governs your existence. You've probably heard dark matter thousands of times. You experience its effects every moment, keeping you anchored to Earth. But here's what most people don't realize. You're living inside something you can't see or detect. Right now, trillions of invisible particles stream through your body like cosmic ghosts. By the end of this journey, you're going to understand why everything you see exists only because of forces completely hidden from perception. Before we dive in, if you find this exploration fascinating, a quick like and subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. This changes everything. At this exact moment, as you sit or stand wherever you are, something extraordinary is happening to your body. Trillions of invisible particles are passing through you, through your skin, your bones, your organs, without you feeling absolutely anything. These aren't ordinary particles. They're not atoms or molecules or anything that could ever show up on any medical scan. They're something far stranger, like cosmic phantoms. These mysterious particles pass through the earth beneath your feet, through the walls around you, through every single thing you've ever touched in your entire life. They exercise a gravitational force so subtle, so perfectly silent, that it shapes the destiny of galaxies spanning hundreds of thousands of light years, yet you remain completely unaware of their presence. These are particles of dark matter, and they represent the most profound mystery in all of science. Dark matter is a substance unlike anything you've ever encountered. It's completely invisible, not just hard to see, but fundamentally unable to interact with light in any way. It doesn't absorb light like a black piece of paper. It doesn't emit light like a star. It doesn't even reflect light like a mirror. Light passes through dark matter as if it simply doesn't exist. Yet this invisible substance composes 27% of everything in the universe. Let me put that in perspective for you. Of all the matter that exists, every star, every planet, every grain of sand, every atom in your body, the stuff you can see and touch, represents less than 1/5 of reality. The other 4/5, completely invisible, utterly undetectable except for one crucial property: gravity. Think about holding a teaspoon in your kitchen. Now imagine that teaspoon could somehow contain dark matter. That tiny spoonful would weigh approximately 400 million tons. That's not a typo. 400 million tons. To help you visualize this impossible density, picture two massive cruise ships, each one the size of a floating city, somehow compressed into the space of a common kitchen spoon. Your mind isn't built to comprehend numbers like that. Neither is mine. But here's what matters. This substance, with its incomprehensible density and invisible nature, surrounds every galaxy in the universe like a vast, unseen ocean. Every galaxy you've ever seen in photographs, the beautiful spirals with their sweeping arms of stars. The elliptical galaxies glowing softly in deep space, they're all floating inside enormous clouds of dark matter. Think of them like cosmic icebergs. The brilliant stars and glowing gas that make galaxies so photogenic represent only the tiny tip that breaks the surface. The real galaxy, the part that actually determines its structure and behavior, is the massive, invisible mountain hiding beneath. Our own Milky Way galaxy sits inside a spherical halo of dark matter stretching 200 light-years in diameter. If our visible galaxy were a 12-inch pizza sitting on your kitchen table, the dark matter halo surrounding it would be an invisible sphere nearly 6 feet across, completely engulfing the pizza. You could walk around that table, examine it from every angle, and see only the pizza, but the invisible sphere would be there, holding everything together with its gravitational embrace. And here's what makes this even more remarkable: without dark matter, galaxies like ours couldn't exist at all. The beautiful spiral arms of galaxies, those sweeping curves of stars that create such stunning cosmic architecture, they're only possible because of dark matter's gravitational scaffolding. Remove the dark matter, and spiral galaxies would tear themselves apart in less than 100 million years. Picture a bicycle wheel spinning rapidly with the metal rims suddenly removed. The spokes would fly outward, the wheel would disintegrate, and you'd be left with scattered pieces spinning off into space. That's exactly what would happen to every spiral galaxy without its invisible dark matter framework. The stars would spread out until they were isolated points of light floating in an empty void, with no galactic structure whatsoever. But dark matter has an almost ghostly quality that sets it apart from anything in your everyday experience. Normal matter, the atoms that make up your body, the air you breathe, the ground beneath your feet, all of it interacts and collides. When you bump into a wall, atoms push against other atoms. When water boils, molecules collide and transfer energy. Dark matter doesn't behave this way at all. Dark matter particles pass through each other as if they don't exist. They experience no friction, no resistance, no collisions whatsoever. It's as if each particle exists in its own private universe, aware only of gravity, but blind to everything else. If we could somehow develop the ability to see dark matter, the night sky would be transformed into something unimaginably beautiful and strange. Instead of seeing isolated points of starlight against black emptiness, we would see a vast cosmic web. Gigantic filaments of dark matter would stretch between galaxies like the strands of an enormous spider's web, connecting every structure in the universe into a single, unified architecture. This invisible scaffolding governs where new galaxies are born and how they evolve over billions of years. It's the hidden blueprint that determines the large-scale structure of everything we see. Even here in our quiet neighborhood of space, dark matter surrounds us. The density of dark matter in our solar system equals just a few protons per cubic meter. That might sound like almost nothing, but remember, this invisible substance makes its presence known through gravity. We can measure its effects on the orbits of planets and the trajectories of spacecraft. It's here, it's real, and it's influencing the motion of everything around us. This has led scientists to construct some of the most sensitive and sophisticated detection equipment ever built, deep underground, buried 1.5 miles beneath the Earth's surface. Laboratories like Lux Zeppelin operate massive tanks containing 10 tons of liquid xenon cooled to 100 degrees C. These underground chambers are shielded by a mile of solid rock to block cosmic rays and other interference. The scientists are waiting, hoping to capture the microscopic flash of light that would occur if a single dark matter particle collides with a xenon nucleus. They're hunting for ghosts, invisible particles that might interact with normal matter perhaps once in a billion collisions. The leading candidates for dark matter particles are called WIMPs, weakly interacting massive particles. These theoretical particles would have a mass roughly 500 times greater than a proton, but they would interact with normal matter so rarely that trillions could pass through your body every second without ever touching a single atom. They represent the perfect suspects because they would interact gravitationally, which explains the astronomical observations, while remaining completely invisible to light and nearly impossible to detect directly. But WIMPs aren't the only possibilities. New theories suggest dark matter might consist of axions, particles so tiny they're billions of times smaller than electrons, or perhaps primordial black holes that formed in the very first moments after the Big Bang. When the universe was still too young for stars to exist, in 2024, The Fermi Space Telescope detected something that sent ripples of excitement through the physics community. High-energy gamma rays with a specific energy signature, 20 giga-electron volts, were observed forming a perfect halo around the center of our galaxy. This radiation appeared exactly where theoretical models predicted dark matter particles might be colliding and annihilating each other, potentially giving us the first direct evidence of dark matter interactions. Every single second, approximately 100 billion dark matter particles pass through each square centimeter of Earth's surface. That's every square centimeter, your hand, your face, this room, every building on the planet. They're all being constantly bombarded by this invisible cosmic rain that never stops, never slows down, and never leaves any trace we can detect. This bombardment isn't harmful. These particles pass through you so effortlessly that they might as well not exist from your biological perspective. But from a cosmic perspective, they're the hidden architects of reality. Dark matter's gravitational influence controls how gas collapses inside galaxies, creating the gravitational wells where hydrogen concentrates and new stars are born. It determines the timing and location of stellar formation throughout cosmic history. When cosmologists run computer simulations of the universe, tracing the evolution of matter over 13.8 billion years, they discover something sobering. If you include only normal matter in these simulations, the universe remains almost completely empty. No galaxies form, no large structures develop, just scattered atoms drifting through an endless void. Only when dark matter is included do the simulations reproduce the rich, complex universe we actually observe. The galaxies, the clusters, the cosmic web of interconnected structures, all of it depends entirely on this invisible foundation. This discovery represents the greatest revolution in physics since Einstein's relativity and the development of quantum mechanics. It forces scientists to confront a humbling reality. The fundamental nature of 95% of the universe remains completely unknown. We're compelled to search for an entirely new physics beyond our current standard model of particles. The Planck satellite's observations of the cosmic microwave background, the afterglow of the Big Bang, revealed how microscopic fluctuations in dark matter density grew over 13.8 billion years into the massive structures we see today. Every galaxy cluster, every cosmic void, every filament of the cosmic web can be traced back to tiny quantum variations in dark matter that existed when the universe was only 380,000 years old. And this invisible substance may ultimately determine the fate of everything that exists. Dark matter's gravitational effects are locked in a cosmic competition with dark energy, the mysterious force accelerating the universe's expansion. Depending on properties of dark matter we don't yet understand, the cosmos might expand forever into cold emptiness, or eventually collapse back on itself in a reverse Big Bang. Fritz Zwicky looked through his telescope and saw something that shouldn't exist. The year was 1933. And Zwicky was studying the Coma cluster, a collection of galaxies located 321 million light-years from Earth. What he observed there would shatter our understanding of the universe forever. More than 1,000 galaxies were moving in a cosmic dance that completely violated the known laws of physics. These weren't gentle, predictable, orbital motions. The galaxies in the Coma cluster were traveling at velocities of 1,000 kilometers per second. To put that impossible speed in perspective, imagine each galaxy as a cosmic artillery shell moving 20 times faster than any spacecraft humanity has ever built. These are entire collections of hundreds of billions of stars, racing through space at velocities that should have torn the cluster apart eons ago. But here's what made Zwicky's observation so disturbing. Based on all the visible matter he could detect in the cluster, these galaxies should have scattered across the universe billions of years ago. Think of it like marbles rolling around on a tray with no edges. With that much kinetic energy and so little visible gravitational binding, the galaxies should have flown off in all directions, leaving nothing but empty space where we now observe a dense, cohesive cluster. Zwicky did the calculations. He added up all the visible stars, all the glowing gas, everything that emitted light in the coma cluster. The math was inescapable and terrifying. To keep these rapidly moving galaxies gravitationally bound together, there would need to be 400 times more mass than what he could actually see. It was like discovering that a 50-story skyscraper was somehow standing on a foundation you couldn't see, but which had to exist to explain why the building wasn't collapsing. The visible matter was just the tip of an invisible iceberg. Zwicky coined a German term for this missing mass: dunkle Materie, dark matter. He was creating a name for something that defied every detection instrument available at the time. Matter that exerted gravitational force but emitted no light whatsoever. It seemed impossible, absurd, like something from science fiction rather than serious astronomy. And perhaps that's why, for the next 40 years, Zwicky's discovery was largely ignored by the scientific community. Like many revolutionary ideas that challenge fundamental assumptions, dark matter was rejected for seeming too improbable. Zwicky found himself fighting alone for decades to defend an observation that most astronomers simply couldn't accept. But Zwicky's problems weren't limited to the cluster as a whole. When he examined individual galaxies within coma, he found that they too showed anomalous orbital velocities. It wasn't just that the cluster needed invisible mass to hold it together. Each galaxy appeared to be surrounded by something that couldn't be observed directly. The mystery was fractal, appearing at every scale of observation. Modern X-ray telescopes would later reveal that the coma cluster contains gas heated to temperatures of 100 million degrees Celsius. That's 7 times hotter than the core of the Sun. This superheated gas between the galaxies emits intense X-ray radiation, creating a cosmic furnace held together by gravitational forces of mysterious and invisible origin. When astronomers finally developed the technology to make precise measurements of the coma cluster, Zwicky's impossible conclusion was confirmed and made even more dramatic. The cluster contains only 5% normal matter, the kind of atoms that make up stars, planets, and everything familiar to us. The other 95% consists of dark matter and dark energy, making coma a perfect example of just how invisible and mysterious our cosmos really is. If you could somehow remove all the dark matter from the coma cluster, it would disintegrate in a matter of millions of years. Like pulling the mortar from a brick wall, the individual galaxies would spread outward in an irreversible expansion toward absolute emptiness. The entire structure exists only because of its invisible foundation. The Hubble Space Telescope later revealed gravitational distortions around the coma cluster that provided direct evidence of this invisible mass. Light from distant background galaxies is bent and warped by the cluster's gravity, creating gravitational lenses that function like cosmic magnifying glasses. These distortions map out the distribution of mass, including the dark matter that can't be seen any other way. But Zwicky's discovery was just the beginning. As astronomers studied galaxies more systematically, they uncovered what became known as the galaxy rotation problem. When you look at spiral galaxies, beautiful pinwheel structures with sweeping arms of stars, something strange becomes apparent when you measure how fast different parts are rotating. According to Newton's laws of gravity, stars farther from the galactic center should orbit much more slowly than stars closer in. Just like planets in our solar system, where distant Neptune crawls along its orbit while inner Mercury races around the Sun. But that's not what astronomers found. Take the Andromeda galaxy, our nearest large galactic neighbor. Stars located 50,000 light-years from the center, way out in the galactic suburbs, are orbiting at 250 kilometers per second. According to classical physics, these peripheral stars should be moving at only 50 kilometers per second, at their observed speeds. They should be ejected into intergalactic space, like rocks thrown too fast from a slingshot. Yet there they are, held in stable orbits by what? This phenomenon became known as flat rotation curves, and it emerged as the universal signature of dark matter's presence, instead of velocities decreasing with distance as predicted by physics. Stellar speeds remain essentially constant out to the observable edges of virtually every galaxy we can measure. The scope of this mystery is staggering. The dark matter problem manifests at every scale, from dwarf galaxies containing only 100 million stars to giant clusters containing thousands of entire galaxies. It's not a quirk affecting only large structures or only small ones. It's a fundamental feature of how gravity works in our universe. This is where Vera Rubin enters the story. Starting in the 1970s, Rubin spent decades collecting observational data that would definitively confirm Zwicky's discovery on a universal scale. Using sensitive spectrographs, she measured the velocities of hundreds of galaxies, building irrefutable evidence that dark matter exists everywhere we look. Rubin's work was meticulous and exhaustive. Galaxy after galaxy showed the same impossible pattern. Stars at the edges moving just as fast as stars near the center. There was no way to explain this with visible matter alone. Every observation demanded the presence of vast amounts of invisible mass. Meanwhile, computer simulations were revealing just how crucial dark matter is to cosmic structure formation. Supercomputers running billions of gravitational calculations showed that galaxies and clusters could never form without this invisible scaffolding. When scientists run these n-body simulations using only normal matter, the universe remains essentially empty. Only when dark matter is included do the simulations reproduce the rich, complex structures we actually observe. These simulations revealed that dark matter follows fractal patterns extending from galactic scales to cosmic filaments. Like a cosmic spider web, dark matter forms hierarchical structures where small halos group together into progressively larger structures, creating the invisible architecture that determines where galaxies form and how they evolve. One of the most compelling pieces of evidence came from studying collisions between galaxy clusters. The Bullet cluster, formed by the collision of two massive clusters, provided a smoking gun for dark matter's existence. During the collision, the normal matter, hot gas, slowed down due to friction and electromagnetic interactions, but the dark matter passed right through. Continuing on its trajectory as if the collision never happened, this proved that dark matter interacts only gravitationally, passing through normal matter and even through itself, without any electromagnetic or strong nuclear interactions. It's truly ghostly in its behavior, affecting the universe through gravity alone. Modern measurements of the ʻOumuamua cluster, the same structure that puzzled Zwicky 90 years ago, confirm that his impossible conclusion was correct. We live in a universe dominated by invisible forces that we're only beginning to understand. What started as one astronomer's strange observation has evolved into the discovery that everything we can see and touch represents only a tiny fraction of all the matter that exists. The first crack in our understanding of reality has revealed that our familiar, visible universe is just a small island floating in an ocean of darkness. This revelation would fundamentally change how we see our place in the cosmos. We're not inhabitants of a universe made primarily of stars and planets and familiar matter. We're residents of a reality that is overwhelmingly invisible, mysterious, and governed by forces we can barely detect. The comfortable, well-understood cosmos that Zwicky thought he was studying in 1933 turned out to be just the visible surface of something far stranger and more vast than anyone had ever imagined. The discovery that our familiar, visible universe is just the surface of something far stranger would soon take on an even more personal dimension. As astronomers turned their instruments toward individual galaxies, they found that the dark matter mystery wasn't confined to distant clusters. It was everywhere, including right here in our own cosmic neighborhood. The Andromeda galaxy became the perfect laboratory for studying dark matter in detail, located just 5 million light-years away. Our nearest large galactic neighbor is close enough for astronomers to make precise measurements of stellar velocities in its outermost regions. This proximity would prove crucial for understanding how dark matter shapes individual galaxies. In the 1970s, Vera Rubin and Kent Ford developed sophisticated spectrographs that could detect the most minute changes in starlight, like cosmic radar systems. These instruments measured the Doppler shift of light emitted by stars, microscopic changes in frequency that revealed whether stars were moving toward us or away from us as they orbited their galactic center. What they found in Andromeda was impossible, according to everything we thought we knew about gravity and orbital mechanics. Stars in Andromeda's outer regions, located 50,000 light-years from the galactic center, were orbiting at 250 kilometers per second. According to Newtonian physics, these peripheral stars should have been crawling along at less than 50 kilometers per second. At their observed speeds, they should have been flung out into intergalactic space long ago. Yet there they were, held in perfect, stable orbits by some invisible force. The rotation curve of Andromeda remained completely flat out to the observable limits of the galaxy. Instead of the expected drop-off in velocity with distance, the speed stayed constant, as if there were an invisible source of gravity distributed uniformly throughout the galaxy. It was like discovering that the outer edge of a spinning record was rotating just as fast as the area near the center, defying everything we know about rotational physics. But this mystery wasn't limited to distant Andromeda. Our own Milky Way galaxy is surrounded by a massive halo of dark matter extending 200,000 light-years in diameter. If we could somehow see this invisible halo, it would occupy an area in the sky 400 times larger than the full moon, completely enveloping our visible galaxy like a vast, unseen cocoon. Consider where you are right now. As you sit or stand wherever you happen to be, you're traveling through space at 220 kilometers per second. That's the speed at which our entire solar system orbits the center of the Milky Way. This velocity is maintained constant by the gravitational influence of dark matter that comprises 90% of our galaxy's total mass. Think about that for a moment. Everything familiar to you, the sun, the planets, every star you can see in the night sky, represents only 10% of the mass of our galaxy. The other 90% is completely invisible. Yet it's what keeps our solar system in its stable orbit and prevents us from either spiraling into the galactic center or flying off into the void. The dark matter mystery becomes even stranger when we examine the small satellite galaxies that orbit the Milky Way. Take the Draco Dwarf Galaxy, one of our galactic companions. This tiny galaxy contains 99% dark matter and only 1% normal matter. It's essentially a cosmic ghost, a few scattered stars floating within an enormous cloud of invisible matter that outweighs the visible stars by 99-1. Scientists have detected this dark matter using a technique called gravitational microlensing. The MACHO project identified events where invisible objects temporarily amplified the light of distant stars. like cosmic magnifying glasses that revealed the presence of dark matter in motion. These fleeting, brightening events provided direct evidence that massive, invisible objects are moving through the halo of our galaxy. Computer models describe how dark matter is distributed using what's called the NFW profile, named after Navarro, Frank, and White. This theoretical framework shows how dark matter density decreases gradually from the galactic core to the edges of the halo. But high-resolution simulations reveal that the structure is far more complex than a simple sphere. Like cities with suburbs and neighborhoods, dark matter halos contain thousands of smaller subhalos, remnants of dwarf galaxies and star clusters that were absorbed over billions of years. These simulations show a rich, hierarchical structure, invisible to telescopes, but crucial to understanding how galaxies form and evolve. Yet this creates a puzzling discrepancy known as the missing satellites problem. Computer models predict that the Milky Way should be surrounded by hundreds of small dwarf galaxies. But we observe only a few dozen. Either our understanding of dark matter is incomplete, or some process is systematically destroying small galaxies faster than we expected. The stability of spiral galaxy structures provides another piece of the dark matter puzzle. Barred spiral galaxies like our own Milky Way maintain their central bar structures for billions of years. Without dark matter, these elegant formations would quickly dissolve due to gravitational resonances. Yet they persist throughout cosmic history. Our galaxy's thick disk contains ancient stars that witnessed galactic collisions in the distant past. These stellar relics preserve evidence of how merger events with smaller galaxies have disturbed the distribution of dark matter over billions of years. They're like geological layers that tell the story of our galaxy's violent history. You can actually see evidence of this galactic cannibalism in the night sky. Stellar streams like the Sagittarius Stream, narrow rivers of stars stretched across the sky, reveal how the Milky Way's dark matter halo is slowly tearing apart its smaller companions. These stellar rivers show the invisible gravitational forces at work, slowly shredding satellite galaxies and incorporating their stars into our own. At the very heart of our galaxy lies Sagittarius A, a supermassive black hole containing 4.3 million times the mass of our Sun. Observations of stars orbiting close to this central black hole have confirmed its mass through relativistic orbital mechanics. Some stars complete their orbits in just 16 years, reaching speeds of nearly 5% the speed of light at closest approach. Different stellar populations throughout the galaxy trace different components and evolutionary phases. Young stars in the thin disk are rich in heavy elements produced by previous generations of stars, while ancient halo stars are metal-poor, preserving the chemical conditions of the early universe. This metallicity gradient, the way heavy element abundance decreases with distance from the galactic center, reveals how elements produced in supernovae have spread throughout the galaxy over 13 billion years of evolution. It's a chemical fingerprint of how our galaxy has grown and changed over cosmic time. Globular clusters orbit through the Milky Way's halo like fossils from the galaxy's formation era. These dense stellar cities contain hundreds of thousands of stars that were born simultaneously and preserve the conditions of the primitive universe virtually unchanged. They're time capsules that help us understand how galaxies formed when the universe was young. The differential rotation of the galactic disk creates persistent spiral density waves that maintain the galaxy's beautiful spiral arm structure, like waves on water that keep their shape while individual molecules move through them. The spiral arms persist while individual stars flow in and out of them over millions of years. This intricate dance is choreographed by dark matter. Without its gravitational framework, The delicate spiral structure would wind up and disappear within a few 100 million years. The fact that we see spiral galaxies throughout cosmic history tells us that dark matter has been providing this invisible scaffolding for billions of years. As astronomers studied galaxy after galaxy, a universal pattern emerged. Regardless of size, type, or age, every single galaxy shows clear evidence of being dominated by invisible matter that determines its structure and evolution. From the smallest dwarf galaxies to the largest ellipticals, the signature of dark matter is unmistakable and universal. The mystery that began with Fritz Zwicky's impossible observation of the Coma cluster had revealed itself to be a fundamental feature of every galaxy in the universe. We weren't dealing with an anomaly or a special case. We were confronting a new reality where the visible universe is just a small decoration floating within invisible architecture that governs everything we see. This realization about dark matter's universal presence would soon expand beyond individual galaxies to reveal an even grander and more mysterious cosmic structure. When astronomers stepped back to examine the largest scales of the universe, they discovered that dark matter had orchestrated something breathtaking and vast, a cosmic architecture that connects every galaxy through invisible threads spanning billions of light years. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies within regions stretching 10 million light-years across. They represent natural laboratories for studying dark matter at the most extreme scales imaginable. The Coma cluster, where Fritz Zwicky first detected the dark matter mystery, contains more than 1,000 galaxies packed into a region roughly the size of 20 Milky Ways placed side by side. If our galaxy were a single city, the Coma cluster would be an entire country filled with similar cities, all interacting gravitationally in a complex cosmic dance orchestrated by invisible forces. Between these galaxies lies something remarkable: gas heated to 100 million degrees Celsius. 7 times hotter than the core of our Sun. This superheated plasma fills the space between galaxies and emits intense X-ray radiation detectable by space-based telescopes. The very existence of this furnace-hot gas reveals the presence of deep gravitational wells created by enormous concentrations of dark matter. What makes galaxy clusters such powerful laboratories is that we can measure their total mass using 3 completely independent methods, and all 3 give consistent results. First, we can measure how fast the galaxies are moving. Second, we can determine the temperature of the hot gas. Third, we can analyze how the cluster's gravity bends light from more distant galaxies. When all 3 methods point to the same answer, confirming that 85% of each cluster's mass is invisible dark matter, the conclusion becomes unavoidable. The most dramatic evidence came from studying collisions between galaxy clusters. The Bullet cluster provided what scientists call a smoking gun for dark matter's existence. When 2 massive clusters collided at thousands of kilometers per second, something extraordinary happened that separated normal matter from dark matter in a way that could be directly observed. During the collision, the hot gas, normal matter that interacts electromagnetically, slowed down due to friction and pressure. You could see this in X-ray images as the gas was stripped away from the galaxies, but the dark matter behaved completely differently. It passed right through the collision zone as if nothing had happened, continuing on its original trajectory without any deceleration or interaction. This collision literally pulled apart normal matter and dark matter, allowing astronomers to map their separate distributions. The galaxies, embedded in their dark matter halos, sailed through the collision unimpeded, while the gas lagged behind, It was direct visual proof that dark matter interacts only gravitationally, passing through normal matter and even through itself like cosmic ghosts. Galaxy clusters also function as gravitational lenses on a massive scale, creating some of the most spectacular distortions in the universe. The immense mass of a cluster, mostly dark matter, curves spacetime so severely that it acts like a natural telescope, amplifying and distorting light from even more distant galaxies. These gravitational lenses create giant arcs and multiple images of background galaxies, stretched and magnified by the invisible mass of the cluster. The cluster, MAX J1149, acts as a cosmic magnifying glass with 50 times amplification, allowing us to observe galaxies so distant they would be completely invisible even to our largest telescopes without this natural boost. The distribution of clusters reveals the universe's largest organizational principle. Clusters aren't randomly scattered through space. They're connected by an invisible cosmic web. Our own local supercluster, which contains the Milky Way, spans 100 million light-years and includes dozens of smaller groups and clusters, all connected gravitationally through filaments of dark matter. Somewhere in the direction of the constellation Centaurus lies a gravitational anomaly known as the Great Attractor. This massive concentration of dark matter, located 250 million light-years away, is pulling our entire region of the universe toward it at 600 kilometers per second. Thousands of galaxies are flowing toward this invisible mass like water flowing downhill, their motion revealing the presence of gravitational forces we can't directly observe. The scale of mass involved in rich galaxy clusters defies comprehension. The largest clusters can contain up to 1,000 trillion solar masses worth of dark matter. To put that impossible number in perspective, that's equivalent to 200 million galaxies, like the Milky Way, compressed into a relatively small region of space. The temperature of the hot gas within clusters provides a direct thermometer for measuring the depth of the gravitational wells created by dark matter. Hotter gas indicates deeper potential wells created by greater concentrations of invisible mass. This allows astronomers to map the distribution of dark matter throughout the cluster, revealing its three-dimensional structure. Cluster collisions occur at velocities of thousands of kilometers per second, releasing energy equivalent to trillions of supernovae. These cataclysmic events can be observed through shock waves propagating through the hot intracluster gas, creating cosmic laboratories where the laws of physics play out on scales impossible to reproduce anywhere else. The Sunyaev-Zeldovich effect allows astronomers to detect galaxy clusters regardless of their distance. When photons from the cosmic microwave background pass through hot cluster gas, they gain energy from interactions with high-energy electrons. This creates a spectral distortion that can reveal clusters even at the edge of the observable universe. Providing a census of how structure has evolved throughout cosmic time, galaxy clusters contain three distinct components in well-defined proportions that tell a consistent story. Approximately 85% of the mass is dark matter, 12% is hot intergalactic gas, and only 3% consists of the stars within individual galaxies. These proportions remain remarkably constant across different clusters, suggesting fundamental physics governing how ordinary and dark matter interact on cosmic scales. The spatial distribution of clusters traces the large-scale structure of the universe like cities connected by highways. Clusters preferentially form along cosmic filaments separated by vast voids that are almost completely empty. This cosmic web architecture reflects how dark matter has organized itself over billions of years of gravitational evolution. Computer simulations like the Millennium simulation have reproduced the observed hierarchy of cosmic structures by tracking how microscopic fluctuations in dark matter density grew over 13.8 billion years. These simulations show that only dark matter can create the complex web of filaments and clusters we observe in the real universe. But something has changed in recent cosmic history. The growth of structure has slowed dramatically over the past 5 billion years as dark energy began dominating cosmic expansion. This cosmic acceleration prevents gravitational collapse, fundamentally altering how structures evolve in the late universe and affecting the formation of new clusters. Even within rich clusters, hundreds of invisible dwarf galaxies dominated by dark matter may be lurking undetected. These ghost galaxies can only be found through their subtle gravitational effects on brighter neighbors during close encounters. They represent a hidden population that could outnumber visible galaxies by huge factors. The abundance of clusters at different masses and different cosmic epochs provides sensitive tests of cosmological models. The cluster mass function constrains fundamental parameters like the density of dark matter and dark energy. Any theory about the nature of dark matter must accurately predict not just that clusters exist, but exactly how many clusters of each size should exist at each epoch in cosmic history. Future space missions, like the Euclid Telescope and the Nancy Grace Roman Space Telescope, will conduct complete censuses of galaxy clusters out to cosmological distances. These surveys will map millions of clusters and test theories about dark matter physics with unprecedented precision, potentially revealing new clues about the nature of this invisible foundation of cosmic structure. Galaxy clusters represent the culmination of dark matter's architectural triumph, massive cathedrals of invisible matter containing thousands of galaxies, each itself embedded in its own dark matter halo. They show us that the mysterious substance first detected by Zwicky doesn't just affect individual galaxies or small groups, but orchestrates structure formation on the very largest scales the universe allows. From this cosmic perspective, a new picture emerges of reality's true architecture, one where visible matter serves merely as decoration on an invisible framework that spans the observable universe. But to truly map this hidden cosmic web, astronomers needed to develop techniques that could reveal dark matter directly. The solution came from one of Einstein's most elegant predictions. In 1915, Albert Einstein made a prediction that would revolutionize our understanding of gravity and space-time itself. He proposed that massive objects don't just attract other objects through some mysterious force, they actually curve the fabric of space-time, creating natural gravitational lenses that bend and focus light like cosmic telescopes. This radical reimagining of gravity as geometry rather than force would fundamentally transform how we perceive the universe around us. Picture a bowling ball placed on a stretched rubber sheet. The heavy ball creates a depression in the elastic surface, causing marbles rolled nearby to follow curved paths around the distortion. The steeper the depression, the more dramatically the marble's trajectories bend as they encounter the warped geometry. In precisely the same way, massive concentrations of dark matter deform the fabric of space-time itself, forcing light rays to follow bent trajectories as they travel across the cosmos. This seemingly abstract concept would become one of our most powerful tools for mapping the invisible universe, transforming theoretical physics into practical astronomy. Einstein's field equations predicted that light itself would be deflected by massive objects, bending around them like water flowing around a boulder in a stream. The amount of deflection would depend on the mass of the lensing object and the precise alignment between the source lens, and observer. This prediction represented a complete departure from Newton's conception of gravity as a force between objects, instead describing it as a consequence of curved space-time geometry. For decades, Einstein's prediction remained a theoretical curiosity, impossible to test with available technology. Astronomers lacked the sensitivity to detect the subtle distortions that gravitational lensing would create, and the mathematics required to interpret such observations were forbiddingly complex. The first tentative confirmations came during solar eclipses, when starlight bending around the sun could be measured against the background stars. But these observations were limited to our immediate cosmic neighborhood. Then, in 1979, astronomers made a discovery that seemed impossible at first glance. They found two nearly identical images of the same distant quasar, designated Q0957+561, separated by just 6 seconds of arc in the sky. The spectral signatures were identical, the redshifts matched perfectly, and even the subtle variations in brightness occurred simultaneously in both images. What they were actually observing was a single quasar, whose light had been split into two distinct paths by the immense gravity of a massive galaxy positioned precisely between the quasar and Earth. This discovery opened an entirely new window into the invisible universe, providing the first direct method for detecting and mapping dark matter through its gravitational effects on light itself. Suddenly, astronomers possessed a tool that could reveal the presence of matter regardless of whether it emitted, absorbed, or scattered electromagnetic radiation. Dark matter's gravitational signature became visible through the distorted images of background galaxies, like shadows cast by invisible objects. The mathematics underlying gravitational lensing emerged from Einstein's field equations, which describe how mass and energy curve spacetime. When light travels through regions of curved spacetime, it follows the shortest possible path, called a geodesic, through that curved geometry. From our perspective, this appears as if the light ray has been bent or deflected by the gravitational field of the intervening mass. Strong gravitational lensing creates some of the most spectacular and beautiful distortions in all of astronomy. The galaxy cluster Ābul 2218, located billions of light-years from Earth, produces dozens of curved blue arcs scattered like cosmic jewelry across telescopic images. These ethereal crescents and loops are not artistic abstractions, but precise manifestations of Einstein's equations in action. Each luminous arc represents a distant galaxy that has been stretched, magnified, and distorted by the gravity of invisible dark matter within the cluster. These cosmic funhouse mirrors reveal the presence of enormous amounts of mass we could never detect through any other method. The cluster's dark matter halo, extending far beyond the visible galaxies, creates a complex gravitational field that acts like a cosmic lens system. Different regions of this field focus light differently, creating multiple images of the same background galaxy at different positions and magnifications. Some background objects appear as nearly complete Einstein rings, where the perfect alignment of source, lens, and observer creates a circular or oval image surrounding the foreground cluster. The distortions aren't random. They follow precise mathematical patterns that allow astronomers to work backward from the observed shapes to determine exactly how much dark matter must be present and where it's located. It's like being able to determine the shape and weight of an invisible sculpture by studying how it bends the light patterns cast on a wall behind it. This inverse problem requires sophisticated computational techniques and statistical analysis, but the results provide unprecedented maps of dark matter distribution. Advanced modeling techniques use the positions, shapes, and magnifications of dozens of lensed galaxies to reconstruct the three-dimensional mass distribution within galaxy clusters. These models must account for the complex interplay between the cluster's gravitational field and the diverse population of background sources at different distances and redshifts. The resulting dark matter maps reveal intricate substructures within galaxy cluster halos, including smaller dark matter clumps associated with individual cluster galaxies. But gravitational lensing occurs across an enormous range of scales, from the smallest detectable effects to the most dramatic cosmic spectacles. Microlensing events can temporarily amplify the brightness of individual stars when compact objects, possibly dark matter particles, small black holes, or other invisible masses, pass directly in front of more distant stars. These events create characteristic brightness curves with precise mathematical signatures that allow astronomers to determine the mass and velocity of the lensing object. For weeks or months, these cosmic magnifying glasses increase a star's brightness by factors of 10 or even 100 before the alignment shifts and everything returns to normal. The light curves exhibit a distinctive symmetrical rise and fall that cannot be mimicked by any other astrophysical phenomenon, making microlensing an extremely reliable detection method for compact dark matter candidates. These brief brightening events have allowed astronomers to detect invisible objects moving through the halo of our own Milky Way galaxy. Projects like MACHO, Massive Compact Halo Objects, and OGLE, Optical Gravitational Lensing Experiment, monitor millions of stars simultaneously, watching for the telltale signature of dark matter objects passing in front of them. These surveys have revealed that some of the Milky Way's dark matter consists of compact objects, though not enough to account for the entire dark matter component. Microlensing surveys have also discovered numerous exoplanets around distant stars, demonstrating the technique's versatility in detecting objects across a vast range of masses. The same gravitational physics that reveals dark matter can also identify planets orbiting stars thousands of light-years away, creating brief perturbations in the microlensing light curves that betray the presence of planetary companions. The most powerful technique for mapping dark matter on cosmic scales uses weak gravitational lensing, detecting subtle distortions in the shapes of millions of background galaxies. These microscopic distortions are far too small to see in any individual galaxy, but when measured statistically across enormous sky surveys covering millions of objects, they reveal detailed three-dimensional maps of dark matter distribution throughout the universe. Weak lensing effects are typically just a few % distortion in galaxy shapes, requiring extraordinarily precise measurements and careful control of systematic errors. Ground-based telescopes must contend with atmospheric turbulence that constantly changes stellar and galactic shapes. While space-based observations eliminate atmospheric effects but introduce their own instrumental challenges, advanced image processing techniques can extract weak lensing signals even from moderately degraded data, using statistical averaging to overcome noise and systematic uncertainties. It's like detecting the presence of an invisible person in a room by noticing how they slightly bend the light patterns on the wall. No single distortion is visible to the naked eye. But when you analyze millions of light patterns with sophisticated computer algorithms, the cumulative effect reveals the hidden mass distribution with extraordinary precision and detail. This statistical approach transforms weak gravitational lensing into one of the most powerful cosmological tools available to modern astronomy. The Hubble Space Telescope has detected more than 1,000 confirmed gravitational lens systems over its decades of operation. each one functioning as a natural cosmic telescope that allows us to study galaxies so distant they formed when the universe was only 10% of its current age. Hubble's exquisite angular resolution and stable imaging conditions make it ideal for identifying and characterizing gravitational lenses, from dramatic Einstein rings to subtle, weak lensing distortions. These gravitational lenses peer deeper into cosmic history than would be possible with conventional optics alone, essentially giving us time machines that reveal how galaxies looked and behaved in the early universe. The magnification provided by foreground galaxy clusters allows astronomers to study individual star-forming regions in galaxies that would otherwise appear as mere points of light, even to the most powerful telescopes. Some gravitational lenses provide truly extreme magnification that borders on the miraculous. The galaxy cluster MAX J1149 amplifies background objects by factors of 50 to 100 times, creating a cosmic microscope so powerful it can detect individual stars in galaxies located 9 billion light-years away. These highly magnified stars appear as transient point sources that brighten and fade, as gravitational microlensing by individual cluster stars modifies the magnification. Without this natural amplification provided by dark matter's gravitational effects, those distant stars would remain forever invisible even to our most advanced ground-based and space-based telescopes. The Einstein cross represents gravitational lensing at its most mathematically elegant and aesthetically beautiful. This perfect fourfold image of a single distant quasar, created by a precisely aligned elliptical galaxy acting as a gravitational lens, demonstrates how space-time geometry can create seemingly impossible symmetries. The same distant object appears 4 separate times in the sky, arranged in a perfect cross pattern that showcases the mathematical beauty and precision underlying cosmic architecture. These multiple images don't just provide spectacular photographs, they arrive at Earth at slightly different times, because light travels different path lengths through curved spacetime to create each image. These time delays, measured with atomic precision, allow astronomers to use the lensing galaxy as a cosmic ruler to measure the expansion rate of the universe, the famous Hubble constant. When the distant quasar varies in brightness due to internal processes, each of the 4 lensed images brightens at predictable intervals, providing an independent method for calibrating cosmic distances and testing our understanding of universal expansion. The time delay measurements require years of careful monitoring to detect the subtle differences in arrival times between the multiple images. These delays depend on both the geometry of the lensing system and the expansion rate of the universe, making them powerful cosmological probes. Different research groups using various gravitational lens systems have measured the Hubble constant to percent-level precision, contributing to ongoing efforts to resolve tensions between different cosmological measurements. Weak lensing surveys conducted by major astronomical observatories have created the largest and most detailed maps of dark matter distribution ever produced. Statistical analyses of tiny distortions in millions of galaxies reveal the cosmic web in unprecedented detail, creating 3-dimensional maps that show how dark matter filaments connect galaxy clusters across billions of light-years like a vast cosmic circulatory system. The Dark Energy Survey, one of the most ambitious astronomical projects ever undertaken, spent 6 years systematically mapping 300 million galaxies across the southern sky to study weak lensing effects. This massive undertaking created the most comprehensive chart of dark matter distribution ever attempted, covering 1/8 of the entire visible sky and revealing the invisible scaffolding that supports all cosmic structure. The survey's data contains subtle correlations between galaxy positions and shapes that encode information about dark matter clustering across cosmic time. These surveys have revealed that dark matter forms a complex hierarchical structure, with small clumps embedded within larger clumps, which are themselves part of even larger filaments and walls. The cosmic web resembles a three-dimensional spider's web of almost unimaginable complexity, with dark matter filaments stretching across hundreds of millions of light-years while maintaining structural coherence. This hierarchical structure emerges naturally from gravitational instability acting on initially small density fluctuations in the early universe. Gravitational lensing provides crucial tests of dark matter's fundamental properties and behavior. If dark matter particles absorbed, scattered, or interacted with electromagnetic radiation in any way, this would create detectable spectral signatures in lensed images. Specific wavelengths of light would be affected differently, creating observable anomalies in the colors and spectra of background objects. But despite decades of increasingly sensitive observations, no such anomalies have ever been found, confirming that dark matter interacts only gravitationally and remains truly invisible to all forms of electromagnetic radiation. This technique also allows scientists to rigorously test alternative theories that attempt to explain galactic dynamics without invoking dark matter. Modified gravity theories like MOND, modified Newtonian dynamics, and other proposals make specific, testable predictions about how lensing patterns should appear if gravity simply behaves differently on large scales, rather than requiring invisible matter. So far, every gravitational lens observation supports the existence of dark matter and contradicts attempts to explain cosmic structure through modifications to gravitational laws alone. Sophisticated mathematical techniques like the Kaiser-Squires method and more advanced algorithms convert observed distortion patterns into detailed mass maps, essentially reconstructing the three-dimensional distribution of dark matter at different distances and cosmic epochs. These computational tools work backward from the distorted light to reveal the invisible mass distribution that caused the distortions, like archaeologists reconstructing ancient structures from scattered fragments. Modern weak lensing analysis employs machine learning algorithms and artificial intelligence to extract maximum information from survey data. These techniques can identify subtle patterns in galaxy shapes that traditional analysis methods might miss, pushing the precision of dark matter mapping to new limits. Deep learning networks trained on simulated data can distinguish genuine lensing signals from instrumental artifacts and atmospheric effects with remarkable accuracy. Weak gravitational lensing has detected extended dark matter halos around individual isolated galaxies, confirming that every galaxy, from the smallest dwarfs to the largest ellipticals, sits within a vast envelope of invisible matter. By measuring subtle distortions of background galaxies visible through and around foreground objects, astronomers have verified that dark matter halos are universal features of cosmic structure. Not limited to galaxy clusters or other special environments, the Euclid Space Telescope, launched in 2023, represents the next generation of precision, dark matter mapping technology. This sophisticated observatory will measure the shapes and positions of 1.5 billion galaxies with unprecedented accuracy to create the most precise census of dark matter distribution ever achieved. Euclid will systematically survey 1/3 of the entire sky, mapping the cosmic web with detail and precision that will revolutionize our understanding of how dark matter shapes cosmic evolution. Euclid's advanced instrumentation includes both visible and near-infrared cameras, optimized for weak lensing measurements, along with a sophisticated spectrometer for measuring galaxy redshifts. The combination of precise shape measurements and three-dimensional positions will enable tomographic reconstruction of dark matter structure across cosmic time, revealing how the cosmic web has evolved since the early universe. Caustic patterns created by complex gravitational lensing produce intricate brightness variations that reveal substructure within dark matter halos at scales much smaller than entire galaxies. Like the ever-changing patterns of light and shadow created by water waves focusing sunlight at the bottom of a swimming pool. These gravitational caustics allow astronomers to detect dark matter subhalos and clumps with masses far below what conventional techniques can resolve. They provide a unique window into the smallest scales of dark matter clustering and structure formation. Variable quasars located behind gravitational lenses provide extraordinarily sensitive probes of dark matter halo structure and particle physics. As distant quasars naturally fluctuate in brightness due to internal processes around their central supermassive black holes, these variations are modified by microlensing effects from compact objects within the foreground lensing galaxy. The resulting complex light curves contain encoded information about the nature, masses, and size distribution of dark matter particles, potentially revealing whether dark matter consists of elementary particles or more exotic objects like primordial black holes. Type Ia supernovae, the cosmic standard candles used to measure distances throughout the universe, can be gravitationally lensed just like any other distant light source. These stellar explosions provide independent calibration of lensing effects, allowing astronomers to cleanly separate gravitational amplification from intrinsic brightness variations. This creates extraordinarily precise measurements of both cosmic distances and dark matter masses, contributing to our understanding of both cosmic expansion and invisible matter distribution. Perhaps the most exciting prospect for the future involves detecting gravitationally lensed gravitational waves. When gravitational waves from colliding black holes, neutron stars, or other cataclysmic events pass through concentrations of dark matter, they can be focused, defocused, and amplified just like electromagnetic radiation. Next-generation gravitational wave detectors may become sensitive enough to detect these subtle effects, opening an entirely new window into dark matter physics that operates on completely different physical principles than optical astronomy. Each gravitational lens discovered by astronomers acts like a natural telescope constructed from pure dark matter, using the curvature of space-time itself to magnify and distort light in ways that reveal the invisible architecture of the cosmos. These cosmic instruments have transformed dark matter from a purely theoretical abstraction into something tangible that we can map, measure, analyze, and study in ever-increasing detail. Through the elegant physics of gravitational lensing, astronomers have created the first direct images of dark matter's distribution throughout the universe, revealing structures and patterns that would otherwise remain forever hidden. What these maps show us is breathtaking in both scope and beauty, a vast cosmic web of dark matter filaments connecting every structure in the observable universe, creating an invisible foundation upon which all of cosmic evolution depends and which determines the ultimate architecture of everything we see. The density of dark matter within filaments is 5 times greater than the cosmic average, creating rivers of invisible matter flowing through the void. These concentrated streams create preferential corridors where galaxies are born and evolve, channeling the raw materials of cosmic construction along predetermined paths. In 2022, astronomers achieved something remarkable. They photographed a cosmic filament directly, Using 142 hours of telescope observations, they captured an image of ionized gas extending 700,000 light-years between two distant quasars. This bridge of glowing matter revealed, for the first time, the invisible architecture that connects the universe, showing us the cosmic web in action. Galaxy clusters form at the nodes of this cosmic web where multiple filaments intersect. Like highway intersections in a giant city, these nodes concentrate thousands of galaxies in regions containing less than 0.1% of the universe's total volume. The gravitational traffic flowing along dark matter filaments all converges at these cosmic crossroads. Mapping this web reveals a fundamental truth about cosmic evolution. Galaxies form preferentially along filaments, like cities built along rivers. Approximately 60% of all galaxies reside within cosmic filaments, while only 5% can be found in the empty voids between them. This cosmic geography determines where star formation occurs and how galactic ecosystems develop. Streams of cold hydrogen gas flow through these filaments, like arteries carrying fuel to living organisms. These currents of raw material keep galaxies alive by providing the continuous supply of gas needed for ongoing star formation over billions of years. Without this cosmic circulation system, galaxies would quickly exhaust their fuel and become barren collections of aging stars. The gas within cosmic filaments reaches temperatures of 1 million degrees Celsius, heated by gravitational compression as dark matter concentrates. This superheated plasma emits faint X-ray radiation that traces the location of invisible structures throughout space, providing a way to map the cosmic web even where no galaxies are visible. Hidden behind the disk of our own galaxy lies a gravitational anomaly called the Great Attractor. This massive concentration of dark matter, located 250 million light-years away, pulls our entire local region of the universe toward it at 600 kilometers per second. Thousands of galaxies are flowing like water toward this invisible gravitational drain, their motion revealing forces we cannot directly observe. Superclusters align along filaments like beads on a cosmic necklace. The coma sculptor complex forms a chain of connected structures held together by dark matter, extending more than 1 billion light-years across the observable universe. These are among the largest coherent structures that physics allows to exist. The cosmic microwave background radiation, the afterglow of the Big Bang, preserves the signature of the tiny fluctuations that seeded this vast architecture. Temperature variations of just 0.0001 degrees across the sky reveal the primordial seeds that grew over 13.8 billion years to form every structure we see today. These ancient patterns are like fossilized fingerprints of the dark matter fluctuations that would eventually build the cosmic web. Future space missions will map this architecture with unprecedented detail. The Euclid Telescope and Nancy Grace Roman Space Telescope will create three-dimensional maps of dark matter distribution by observing 1 billion galaxies. These surveys will reveal the cosmic web with precision never before achieved in the history of astronomy. The hierarchical structure of the universe reflects different epochs of gravitational collapse stretching back to cosmic dawn. Small dark matter halos formed first, then gradually merged into progressively larger structures, creating a cosmic family tree that connects every galaxy to the primordial history of the universe. Each structure we see today carries the memory of billions of years of cosmic evolution. This cosmic web isn't static. It's constantly evolving as gravity continues its patient work of building structure. Dark matter streams along filaments, feeding the growth of galaxy clusters at intersection points. Over cosmic time, small structures merge into larger ones, gradually building the hierarchy of cosmic architecture we observe today. The discovery of this cosmic web has fundamentally changed our understanding of the universe's organization. What once appeared to be randomly scattered galaxies are actually following a hidden blueprint written in dark matter. Every star, every planet, every atom in your body exists within this vast architectural framework that spans the observable cosmos. The cosmic web reveals that we live in a universe governed entirely by invisible forces. Our familiar reality, stars, planets, life itself exists only in the nodes and filaments of a gigantic structure made of matter we have never directly detected. Everything visible represents mere decoration on an invisible foundation that extends across the deepest reaches of space and time. This realization sets the stage for an even more disturbing discovery that would shake the foundations of cosmology itself. Recent observations suggesting that this dark matter framework may not be as stable and eternal as we once believed. In 2024, the Dark Energy Spectroscopic Instrument Project made a discovery that sent shockwaves through the foundations of modern cosmology. After mapping 40 million galaxies using 5,000 robotic optical fibers, scientists detected something that should have been impossible. Dark matter appears to be losing its grip on the universe over the past 5 billion years. This wasn't just an incremental finding that refined existing models. It was a fundamental challenge to everything we thought we understood about cosmic evolution. The culprit appears to be dark energy, the mysterious force that accelerates the expansion of the universe. For 25 years, astronomers had assumed dark energy was a cosmological constant, unchanging throughout cosmic history. But the new DESI data suggests something far more disturbing. This force may be evolving and weakening over time, fundamentally altering the balance of power between dark matter and dark energy. If dark energy continues to weaken, the universe might not expand forever as we've long assumed, like a ball thrown upward that eventually succumbs to gravity and falls back down. Cosmic expansion could reverse all the galaxies, all the cosmic web structure built over 13.8 billion years could collapse back into a reverse Big Bang, a big crunch in trillions of years. The implications are staggering. Everything we see around us exists because of a delicate balance between dark matter trying to pull things together and dark energy pushing them apart. If that balance is shifting, it changes the ultimate fate of everything that exists. Type Ia supernovae, the cosmic standard candles that first revealed dark energy's existence, are now showing discrepancies between the early and late universe. These stellar explosions reveal tensions in the standard cosmological model, suggesting that fundamental physics changed somewhere in the universe's recent history. The very tools that discovered dark energy are now questioning its nature. Meanwhile, the James Webb Space Telescope has detected massive galaxies that shouldn't exist in the early universe. Galaxies containing 100 billion stars appear when the universe was only 400 million years old, insufficient time for such complex structures to form, according to current models. These observations suggest our understanding of how dark matter builds structure may be fundamentally incomplete. Adding to the crisis is the Hubble tension, a 10% discrepancy between measurements of cosmic expansion made locally versus predictions from the cosmic microwave background. This represents a fundamental crisis in cosmology. Either our most precise measurements are systematically wrong, or our basic understanding of the universe needs complete reformulation. The search for dark matter particles has led to increasingly exotic candidates. Beyond the traditional WIMPs, scientists now consider axions, particles billions of times smaller than electrons, or primordial black holes that formed in the first 0.0001 seconds after the Big Bang. Each possibility would require completely different detection strategies and imply radically different physics. Deep underground, the Lux Zeppelin experiment uses 10 tons of liquid xenon cooled to extreme temperatures, buried 1.5 kilometers beneath solid rock to shield it from cosmic radiation. This detector represents humanity's most sensitive attempt to capture the microscopic flash of light produced when a single dark matter particle collides with an atomic nucleus. After years of operation, the silence has been deafening. Gravitational wave detectors may have inadvertently detected dark matter in the form of primordial black holes. If dark matter consists partly of black holes with masses around 30 times our Sun, they would explain some of the merger events detected by LIGO. This could solve the dark matter mystery while explaining an unexpected population of stellar mass black holes at the center of our galaxy. Telescopes have detected 511 keV gamma-ray emission that could represent the first direct evidence of dark matter interactions. Light, dark matter particles annihilating in the galactic core would produce this specific energy signature. These observations provide tantalizing hints that dark matter may not be completely invisible after all. Computer simulations reveal another troubling discrepancy. Cold dark matter models predict far more small galaxies around the Milky Way than we actually observe. This missing satellites problem suggests either that dark matter has exotic properties we don't understand, or that astrophysical processes systematically destroy small galaxies faster than expected. Some physicists have proposed abandoning dark matter entirely. Modified Newtonian dynamics, MOND, suggests that gravity simply works differently at extremely low accelerations. While MOND eliminates the need for dark matter in galaxies, it creates intractable problems when applied to galaxy clusters and cosmic structure formation. Precision gravitational lensing studies are testing whether dark matter interacts with itself through forces other than gravity. Collisions between galaxy clusters reveal whether dark matter is perfectly collisionless or has weak self-interactions that would affect its spatial distribution. So far, dark matter appears to be truly ghostly, but increasingly sensitive observations may detect subtle deviations. The Euclid mission will measure the shapes of 1.5 billion galaxies to create the most detailed map of dark matter ever attempted. By detecting microscopic distortions caused by weak gravitational lensing, this survey will test dark matter models with unprecedented precision. If current theories are wrong, Euclid will reveal the discrepancies. Theoretical physicists are exploring scalar field theories, where dark matter represents a quantum field permeating all of space, similar to the Higgs field that gives particles their mass. Such a field could explain dark matter's elusive nature and uniform distribution throughout the cosmos, but would require entirely new physics beyond the standard model. The matter-antimatter asymmetry that allowed normal matter to survive the Big Bang may be connected to dark matter's nature. If dark matter particles are their own antiparticles, annihilation processes in the early universe could have produced the excess of normal matter we observe today. This would link two of cosmology's greatest mysteries through a single mechanism. Space-based detectors like AMS-02 on the International Space Station search for the decay products of dark matter particles, excess positrons, antiprotons, and gamma rays that would signal dark matter's natural radioactive decay. These experiments probe whether dark matter is truly stable or slowly disintegrates over cosmic timescales. Theories involving extraspatial dimensions suggest dark matter may interact through hidden dimensions invisible to us. Explaining why we detect it only gravitationally, string theory predicts additional dimensions where dark matter could reside, potentially explaining its mysterious properties through higher dimensional physics. At the Large Hadron Collider, physicists search for dark matter by looking for missing energy in particle collisions. When protons smash together at nearly light speed, dark matter particles would escape detection, carrying away energy in a way that violates conservation laws unless invisible particles are created. Years of searching have yielded only upper limits on interaction rates. All of these investigations converge on a sobering conclusion. The dark matter crisis represents the greatest mystery in modern physics. With 95% of the universe composed of dark matter and dark energy, we've discovered that our observable reality represents only a microscopic fraction of something vastly larger and completely incomprehensible. We stand at the edge of a cosmic abyss, confronting the possibility that everything we thought we understood about the universe may be fundamentally wrong. The comfortable assumption that we live in a well-understood cosmos has been shattered, revealing a reality far stranger and more mysterious than our wildest imaginations ever conceived. But what does this mean for us? The discovery of dark matter reveals that we are inhabitants of a universe that is overwhelmingly invisible. Like fish swimming in the depths of an ocean who suddenly realize they live within an immensity of water they never noticed. We've come to understand that our visible reality floats within a vastness of undetectable substance that dwarfs everything familiar. Every atom in your body, the iron flowing through your bloodstream, the calcium strengthening your bones, the oxygen filling your lungs with each breath, represents only 5% of the matter in the universe. All the elements that make you who you are, that constitute every living thing on Earth, that form every star and planet you've ever seen, are a microscopic minority in a reality dominated by invisible forces. This isn't just an abstract scientific fact. It's a profound truth about your existence. You depend completely on the invisible architecture created by dark matter. Without the scaffolding of dark matter that enables galaxy formation, there would be no stars to forge heavy elements, no planets to harbor life, no possibility for consciousness to emerge anywhere in the cosmos. Life on Earth exists thanks to a cosmic dance between forces we can never directly detect. Dark matter guided the formation of the Milky Way, positioning our solar system in the galactic habitable zone and maintaining the orbital stability necessary for biological evolution to unfold over billions of years. Every moment of your life is choreographed by invisible hands. As you read these words, trillions of dark matter particles are streaming through your body at this very instant, like an invisible cosmic rain that never stops. You are constantly bombarded by this mysterious substance. You don't feel it. You can't sense it in any way, yet it governs your cosmic destiny more completely than any force you can perceive. Dark matter connects our galaxy to every other galaxy in the universe through a cosmic web of invisible filaments. The Milky Way is gravitationally linked to structures billions of light years away through dark matter threads you'll never see. You are part of something inconceivably vast, a cosmic organism that spans the observable universe. Our understanding of reality is fundamentally limited by the sensory capabilities that evolution gave us. We evolved to detect only the visible fraction of the universe, leaving us blind to 95% of the reality that surrounds and controls us constantly. It's as if we've been living our entire lives wearing glasses that filter out most of the electromagnetic spectrum, leaving us aware of only a tiny sliver of what's actually there. The search for dark matter is pushing human technology to its absolute limits. Detectors buried kilometers underground, cooled to within degrees of absolute zero, represent the most sensitive machines humanity has ever constructed. These instruments can detect the collision of a single subatomic particle, yet they remain silent in the face of dark matter's ghostly presence. If we ever directly detect a dark matter particle, it will rank among the most important moments in the history of physics, comparable to the discovery of DNA or atomic structure. This breakthrough would revolutionize our fundamental understanding of reality itself. It would mark the moment humanity finally made contact with the invisible foundation of everything that exists. Understanding dark matter could unlock technological possibilities currently beyond our imagination, just as quantum mechanics led to computers, lasers, and the digital age. Comprehending dark matter might open doors to technologies we can't even conceptualize today. Perhaps manipulation of dark matter could lead to new forms of energy, revolutionary materials, or even ways to interact with the cosmic web itself. Your position in the universe is simultaneously central and utterly insignificant. While you're made of the rare matter that shines and enables complexity, you exist in a reality dominated by substances that transcend your capacity for direct perception. You're a brief arrangement of cosmic dust, conscious for a few decades in a universe billions of years old, made of atoms that represent a tiny minority of all matter. Human consciousness may be the most improbable phenomenon in a universe dominated by dark matter, in a 13.8 billion-year-old cosmos governed by invisible forces. The emergence of beings capable of questioning their own existence represents something extraordinarily rare. You are matter organized in such a way that it can contemplate its own cosmic insignificance and still find meaning. Each new discovery about dark matter reveals how little we truly know about our own reality. Like explorers mapping an unknown continent, every answer about dark matter generates 10 new questions about the fundamental nature of existence. We're constantly discovering that our ignorance is even more profound than we previously realized. Dark matter teaches us cosmic humility about the limits of human knowledge. After millennia of believing we understood the universe, we've discovered that we're ignorant about 95% of the reality that constantly surrounds us. This isn't a temporary gap in knowledge. It's a fundamental revelation about the nature of reality itself. The future of humanity may depend on understanding the invisible forces that govern us, just as comprehending gravity enabled space travel and understanding electromagnetism led to modern civilization. Deciphering dark matter could be crucial for our survival and expansion as a cosmic species. Our long-term destiny may be written in forces we can't yet detect. Children born today might be the first generation to discover the true nature of dark matter. In laboratories around the world, experiments currently underway could resolve physics' greatest mystery within the next 2 decades. These children might live to see humanity's first direct contact with the invisible foundation of cosmic architecture. Dark matter connects you to the Big Bang in a direct and tangible way. The invisible particles streaming through your body right now may have been created in the first moments of cosmic history, making you a living witness to the universe's creation. You carry within your immediate vicinity the remnants of cosmic dawn. Your curiosity about dark matter represents the fundamentally human drive to understand the incomprehensible. Even knowing it might forever remain beyond our detection capabilities, we persist in the search because questioning our reality is essentially what makes us human. This drive to explore the unknown defines our species more than any other characteristic. The discovery of dark matter has forever changed how we see ourselves in the cosmos. We're no longer the protagonists of a universe designed around us, but temporary inhabitants of a vast, ancient reality dominated by profound mysteries. We exist for the briefest instant in a cosmos that operates according to rules we're only beginning to glimpse. Dark matter reminds us that the universe is stranger, more beautiful, and more mysterious than we ever dared imagine. In an era when we thought we understood nearly everything, it preserves our sense of wonder and keeps us humble before the incomprehensible magnificence of existence. It ensures that no matter how much we learn, the cosmos will always retain its power to amaze and mystify us. This invisible foundation of reality connects every star, every galaxy, every moment of cosmic history into a single, unified whole that transcends our ability to fully comprehend, yet continues to invite us deeper into its endless mystery. We live as luminous beings in a reality that is predominantly dark, in a universe where only 5% of matter emits light. We are rare creatures made of atoms that shine, existing in a vastness dominated by substances we will never see. We are like fireflies flickering briefly in an infinite cosmic night, our light precious precisely because it represents such a tiny fraction of what exists. Think about what this means for your very existence. Every atom in your body, the carbon that forms your DNA, the oxygen flowing through your bloodstream, the calcium in your bones, represents a kind of cosmic aristocracy. You are made of the rare matter that interacts with light, that can bind together into complex molecules, that can organize itself into the intricate biochemistry of life. Yet this luminous matter that makes you possible is a microscopic minority in a universe dominated by invisible substances. Our sensory perception evolved for a universe that represents merely a sliver of total reality. Over billions of years of evolution, we developed eyes to see light, ears to hear sound, nerves to feel pressure and temperature. But we remain completely blind to 95% of the cosmos that surrounds us constantly. We are like beings who evolved to perceive only a single note in a vast cosmic symphony, forever deaf to the greater music playing around us. Consider the profound limitation this represents. Your brain, shaped by millions of years of natural selection, was optimized to help your ancestors find food, avoid predators, and reproduce successfully. It was never designed to comprehend dark matter, extra dimensions, or the fundamental nature of space-time. The fact that we can even conceive of these mysteries represents an extraordinary accident of evolution. Dark matter teaches us that ignorance and mystery are natural states of existence. Even with all our science and technology, our particle accelerators, our space telescopes, our quantum computers, we remain fundamentally like children exploring a cosmic playground whose basic rules we still don't completely understand. Every answer we discover reveals 10 new questions, each more profound than the last. You are a conscious witness to a universe that transcends your capacity for comprehension. Human consciousness represents perhaps the most extraordinary phenomenon in the cosmos. Matter organized so complexly that it can contemplate its own cosmic insignificance and still find meaning. You are atoms that have learned to wonder about themselves, stellar dust that has awakened to question its own existence in a reality it can never fully perceive. Your curiosity about dark matter reveals humanity's deepest drive to seek truths beyond perception. Even knowing dark matter may forever remain beyond our direct detection. We persist in the search because questioning our reality is what fundamentally defines us as a species. This restless questioning, this refusal to accept ignorance as final, may be the most remarkable characteristic of human consciousness. Life on Earth emerged and evolved within an invisible ocean of dark matter. Every moment of biological evolution, from the first self-replicating molecules 3.8 billion years ago to the emergence of human consciousness, occurred while completely immersed in a reality dominated by forces we cannot directly perceive. Every species that ever lived, every extinction event, every evolutionary breakthrough happened within this cosmic context we're only now beginning to glimpse. Your ancestors contemplated the stars without knowing they were surrounded by a predominantly invisible reality. Generations of philosophers, scientists, and poets developed entire cosmologies and systems of meaning based on an incomplete understanding of the universe they inhabited. Ancient Greek philosophers debating the nature of reality, medieval scholars reconciling faith with reason, Enlightenment thinkers discovering natural laws, all were working with less than 5% of the actual picture. Every human culture, every religion, every philosophical system developed while blind to 95% of reality. The pyramids were built within dark matter's invisible architecture. Shakespeare wrote his sonnets while dark matter particles streamed through his body. Einstein developed relativity while surrounded by the very substance that would later challenge his cosmological assumptions. The discovery of dark matter represents a Copernican revolution regarding our cosmic importance, just as we learned that Earth isn't the center of the solar system, that the solar system isn't the center of the galaxy, that our galaxy isn't the center of the universe. We now know that all visible matter is merely decoration on an invisible architecture. We are not the main characters in this cosmic story. We're a brief subplot happening within something incomprehensibly larger. Each breath you take, each heartbeat, each thought occurs while immersed in a reality that transcends your perception. Dark matter isn't something distant happening in remote galaxies. It permeates this moment, this place, your conscious experience of this exact instant of existence. As you read these words, trillions of dark matter particles are streaming through your body, carrying with them the gravitational memory of cosmic structure formation. Our technology has allowed us to detect our own ignorance on cosmic scales. The most sophisticated instruments humanity has ever built, telescopes that can see galaxies billions of light years away, detectors that can sense the collision of a single subatomic particle, have primarily revealed how little we know about the fundamental nature of reality. We've created machines sensitive enough to detect gravitational waves from colliding black holes. Yet we remain completely deaf to the cosmic symphony of dark matter flowing around us. The search for dark matter unites humanity in a common scientific purpose. Regardless of nationality, culture, religion, or political belief, scientists around the world collaborate to solve the greatest shared mystery of our existence. Underground laboratories in Italy work alongside particle accelerators in Switzerland. Space telescopes operated by NASA coordinate with ground-based observatories in Chile. This quest represents humanity at its best, curious, humble, united in the face of the unknown. Each dark matter particle streaming through your body carries the history of the primordial universe. These invisible cosmic travelers may have been created in the first instance after the Big Bang, when the universe was smaller than an atom and hotter than a trillion stars. They connect you directly to the origin of all reality, making you a living witness to cosmic creation. Dark matter preserves our sense of wonder in an age of advanced knowledge. In a world where we can explain the behavior of subatomic particles, predict the weather, and map the human genome, dark matter maintains the fundamental human experience of contemplating the truly mysterious and incomprehensible. It ensures that no matter how much we learn, the universe retains its power to humble and amaze us. Your existence represents an extraordinary improbability in a cosmos dominated by invisible forces. The precise combination of conditions necessary for conscious life to emerge in a predominantly dark reality makes your presence here almost miraculous. Stars had to form in exactly the right way. Heavy elements, had to be forged and distributed. Planets had to develop stable orbits. Complex chemistry had to emerge, all within the invisible scaffolding of dark matter that makes cosmic structure possible. The cosmic humility that dark matter teaches could be transformative for our species. Recognizing our fundamental ignorance about reality might make us wiser, more collaborative, and less arrogant in our ambitions. Understanding how little we know about the cosmos that contains us could paradoxically make us more capable of learning, more open to new possibilities, more respectful of the mystery that surrounds us. Future generations may discover that dark matter is connected to consciousness in ways we cannot currently imagine. Just as quantum mechanics revealed surprising connections between observer and observed, the nature of dark matter might be intertwined with fundamental questions about mind and experience. The invisible foundation of reality might touch consciousness itself in ways we haven't yet conceived. Dark matter connects us to all other possible forms of life in the universe. If consciousness exists elsewhere in the cosmos, it too evolved while immersed in this same invisible architecture, sharing with us this fundamental cosmic condition. Any intelligence anywhere in the universe faces the same overwhelming mystery, the same vast invisibility of reality's foundation. Your mortality gains profound perspective when viewed against dark matter's potential eternity. While you live for decades, the dark matter particles surrounding you may exist for trillions of years, potentially witnessing the birth and death of countless civilizations, the formation and dissolution of galaxy clusters, perhaps even the heat death of the universe itself. You are a brief note in a cosmic symphony that plays across timescales that dwarf not just human history, but the entire lifetime of stars. The experience of being alive in a predominantly invisible reality is profoundly poetic. You are a creature made of light from ancient stellar furnaces, dancing temporarily in a cosmic symphony composed primarily of silence and darkness. Your consciousness is a brief candle flame flickering in an infinite cosmic night, yet somehow capable of contemplating the very darkness that surrounds it. Dark matter reminds us that the universe is infinitely stranger and more beautiful than our imagination could ever conceive. In an era of scientific explanations and technological mastery, it preserves the fundamental mystery that makes existence a continuous adventure of discovery and wonder. It guarantees that reality will always exceed our ability to fully comprehend it, keeping alive the sense of awe that makes us most deeply human. We have reached the end of a journey through the greatest mystery of existence, from Fritz Zwicky's impossible discovery in 1933 to the most recent detections by the James Webb Space Telescope and the Dark Energy Spectroscopic Instrument. We've explored how an invisible substance shapes all the reality we know and experience. This has been more than a story about astronomy or physics. It's been a profound journey into the very nature of what it means to exist in a cosmos dominated by forces beyond our perception. Dark matter is not simply a distant astronomical phenomenon relegated to the depths of intergalactic space. It is the fundamental architecture of your existence, the invisible foundation upon which every moment of your life is built, every heartbeat, every breath. Every thought occurs within this invisible reality that determines where galaxies are born, where stars ignite their nuclear fires, and where planets can harbor the delicate, improbable chemistry of life. You are not separate from this cosmic mystery. You are embedded within it, shaped by it, utterly dependent upon it for your very existence. Let's retrace the remarkable journey that brought us to this understanding. We began with galaxies that refused to behave as they should, refusing to scatter across space according to the laws of physics as we understood them. Fritz Zwicky observed impossible velocities in the Coma cluster, more than 1,000 galaxies moving at speeds that should have torn the cluster apart billions of years ago, revealing the first crack in a reality we thought we understood completely. That single observation opened a window into a cosmos far stranger and more mysterious than anyone had ever imagined possible. Decades later, Vera Rubin confirmed that every individual galaxy floats within an invisible ocean 10 times more massive than all its visible stars combined. Her meticulous measurements of galactic rotation curves revealed flat velocity profiles that defied every prediction of Newtonian physics. What began as an anomaly in distant galaxy clusters became a universal truth about the nature of cosmic architecture. We discovered that we live in a universe dominated by substances that completely transcend our capacity for direct perception. Galaxy clusters and gravitational lensing showed us that dark matter doesn't just surround galaxies, it sculpts the very geometry of spacetime itself. Through careful analysis of how massive clusters distort light from distant objects, we learn to map the distribution of invisible mass that governs cosmic evolution. These cosmic funhouse mirrors, bending and magnifying the light of background galaxies, revealed the hidden skeleton supporting all visible structure throughout the universe. The discovery of the cosmic web unveiled a universal architecture of breathtaking scope and beauty. Filaments of dark matter stretch across hundreds of millions of light years, connecting every structure through an invisible network that functions like the universe's circulatory system. This cosmic web transports matter and energy throughout the cosmos, determining where galaxies are born, how they evolve, and ultimately where planets capable of supporting life can form. We discovered that we inhabit not a collection of isolated islands of matter floating in empty space, but a unified cosmic organism of unimaginable complexity. But our understanding continues to evolve in ways that challenge our assumptions. The current crisis in cosmology suggests that even our hard-won knowledge about dark matter may be incomplete. Recent discoveries about potentially variable dark energy, tensions between different measurements of cosmic expansion, and observations of massive galaxies in the early universe all indicate that even greater revolutions may be approaching. Just when we thought we were beginning to grasp the invisible universe, new observations suggest we may have been seeing only shadows of an even deeper reality. Humanity's response has been to push our technology to its absolute limits. Extreme detection technologies buried kilometers underground represent our most ambitious attempt to capture a single particle of dark matter. These detectors, shielded from cosmic radiation by miles of solid rock and cooled to temperatures approaching absolute zero, represent the most sensitive machines ever constructed by human civilization. They embody our species' relentless drive to touch the untouchable, to make direct contact with the invisible foundation of everything that exists. Our current understanding suggests there are at least 3 fundamentally different types of dark matter candidates. WIMPs, weakly interacting massive particles, represent the traditional favorite. Particles that would interact only gravitationally while remaining invisible to electromagnetic radiation. Axions, hypothetical particles billions of times smaller than electrons, offer a radically different possibility that would require entirely new physics. Primordial black holes, formed in the first fraction of a second after the Big Bang, represent yet another window into completely revolutionary cosmology. Each possibility would fundamentally transform our understanding of particles, forces, and the nature of matter itself. The search for dark matter is uniting humanity in an unprecedented scientific collaboration that transcends national boundaries, cultural differences, and political divisions. International collaborations connect underground detectors in abandoned mines with space telescopes orbiting Earth. Particle accelerators beneath the French-Swiss border with gravitational wave observatories in Louisiana and Italy. Scientists from every continent work together, sharing data, insights, and resources in humanity's greatest collective investigation into the nature of reality itself. Each discovery about dark matter reveals that our ignorance extends far deeper than we previously imagined. Like explorers mapping an unknown continent who discover that every mountain range they chart reveals 10 more ranges beyond it. Every answer we find about dark matter generates dozens of new questions about the fundamental nature of existence. We keep discovering that what we don't know dwarfs what we do know by margins that grow ever larger with each new observation. Dark matter has taught us profound cosmic humility about the limits of human knowledge and perception. After millennia of believing we understood the universe, from ancient cosmologies that placed Earth at the center of creation to modern physics that seem to explain the behavior of matter and energy, we've discovered that we remain profoundly ignorant about 95% of the reality that constantly surrounds us. This isn't simply a temporary gap in our knowledge that will eventually be filled by more sophisticated instruments and cleverer theories. It's a fundamental revelation about the nature of existence itself and our place within it. Your existence as a conscious being in a predominantly invisible universe represents an extraordinary improbability that borders on the miraculous. Consider the precise combination of conditions that had to align for life and consciousness to emerge in a reality dominated by invisible forces. Dark matter had to clump together in exactly the right way to allow galaxy formation. Stars had to form and evolve to produce heavy elements. Planets had to develop stable orbits within habitable zones. Complex chemistry had to emerge from simple atoms. And somehow, against odds so vast they challenged comprehension, matter organized itself into patterns capable of awareness, curiosity, and wonder. Dark matter preserves mystery and a sense of profound wonder in an age of increasingly advanced scientific knowledge. In a world where we can manipulate individual atoms, decode the human genome, predict weather patterns, and communicate instantly across vast distances, dark matter maintains the fundamental human experience of contemplating the truly incomprehensible. It ensures that no matter how much we learn about the mechanics of reality, the universe retains its power to humble us, to remind us that existence itself remains an ongoing mystery. Future generations of children alive today may be the first human beings to discover dark matter's true nature. Experiments currently underway in laboratories around the world, from deep underground chambers to space-based telescopes to the most powerful particle accelerators ever built, could resolve physics' greatest mystery within the next few decades. These children may witness humanity's first direct contact with the invisible foundation that has supported everything we see throughout cosmic history. The complete discovery and understanding of dark matter's nature could unlock technologies as revolutionary as they are currently unimaginable. Just as quantum mechanics led to computers, lasers, transistors, and the entire digital age, understanding dark matter might enable advances that seem like magic from our current perspective. Perhaps manipulation of dark matter could lead to new forms of energy that make fossil fuels seem primitive, revolutionary materials that transform engineering and construction, or transportation technologies that harness the cosmic web itself. Our journey through the invisible universe has connected us directly to both the Big Bang that created everything and the ultimate destiny that awaits the cosmos. The invisible particles surrounding you at this very moment carry within them the history of 13.8 billion years of cosmic evolution. They may ultimately determine whether the universe will expand eternally into cold, empty darkness, or eventually reverse its expansion and collapse back upon itself in a cosmic implosion that ends everything. You exist at the crossroads between cosmic creation and cosmic fate, a temporary witness to an ongoing story of unimaginable scope. Dark matter reminds us that we are temporary inhabitants of a reality that is ancient beyond human comprehension, vast beyond human imagination, and mysterious in ways that challenge our deepest assumptions about existence. We are not the center of the universe, nor its ultimate purpose, but we are conscious witnesses capable of contemplating our own cosmic insignificance and somehow still finding meaning in our brief existence. We are temporary patterns of organized matter that have somehow become aware of the greater pattern in which we are embedded. The human quest to understand dark matter represents our species' most noble impulse to question the fundamental nature of our reality. Even knowing that dark matter may forever remain beyond our direct reach, that we may never fully comprehend the invisible forces that govern us. We persist in the search because seeking truth is fundamentally what defines us as conscious beings. This drive to understand, to push relentlessly against the boundaries of the knowable, to refuse to accept ignorance as a final answer, may be the most remarkable characteristic of human consciousness. The universe has revealed itself to be far stranger, more beautiful, and more mysterious than we ever dared imagine. Dark matter has taught us that to live as conscious beings means to exist permanently at the threshold between the known and the incomprehensible, between the light we can see and the darkness that governs us. We are brief islands of awareness flickering in an ocean of mystery, conscious sparks illuminating for a moment a cosmic night that stretches far beyond anything our minds can fully grasp. Yet somehow finding in that very mystery a source of wonder that makes our temporary existence infinitely precious.